Let's go ahead and get started by taking a look at the IoT and its impact on efficiency requirements. Over the years, the trickle of Internet of Things devices has turned into a deluge. The IoT has now touched our daily lives. Our cars, watches, thermostats, and refrigerators are connected to the Internet. This rise impacts devices in a variety of industries, including automotive, industrial, energy, consumer electronics, aviation, and more. And while the connected nature of these devices leads to convenience and broadens their impact, developing such devices can be challenging due to their resource-constrained nature. Embedded systems have always required resource efficiency, but with ever tighter form factors, power budgets, and cost constraints, the need is growing. Since more code must be added to handle increasing amounts of data, embedded devices for the Internet of Things have to optimize every watt, millimeter, and penny. This webinar will discuss how Datalight's Reliance Edge file system and Micrium's MicroCOS kernel and scheduler were created with these constraints in mind, enabling embedded developers to combat common inefficiencies that plague IoT projects. At Micrium, efficiency has long been a goal of our software developers, and this is reflected in our kernels, MicroCOS 2 and MicroCOS 3. Prospective kernel users are often told that they can make better use of CPU time by writing their application code around a kernel. However, there's certainly no guarantee of efficiency gains in the move from single-task to multitask application code. To realize their CPU's potential, developers must select a kernel that is itself efficient, and they must know how to configure the kernel and write their application code so that it too will use CPU resources efficiently. In this section of slides, we'll see that MicroCOS 2 and MicroCOS 3 are indeed highly efficient kernels in terms of both CPU overhead and memory footprint. We'll also consider some of the configuration parameters that developers can use to increase the memory efficiency of their kernel-based systems. Before examining Micrium's two kernels from an efficiency standpoint, we'll view them at a somewhat higher level, and we'll start with MicroCOS 2. The longtime anchor of Micrium's product lineup, MicroCOS 2 is more than just a multitasking scheduler. It is a proven software platform for the embedded space. Developers who choose MicroCOS 2 can be confident that their kernel will run reliably in the most demanding of systems while using CPU and memory resources efficiently. MicroCOS 2's impressive 18-year track record includes numerous aerospace projects in which customers have taken the kernel through the grueling DO-178B certification process. Use in medical devices certified according to IEC 62304 and industrial systems complying with IEC 61508 likewise comprises part of the kernel's history. For many years, MicroCOS 2 has been offering application developers a familiar set of useful kernel services, including management of semaphores, mutexes, mailboxes, and message queues, in addition to highly efficient task scheduling capabilities. With its large user base and safety-critical systems, the kernel is extremely unlikely to undergo any major changes aimed at adding new features or services, and this is, to a large extent, why Micrium continues to offer two kernels. MicroCOS 2 is an ultra-stable and efficient multitasking solution that is especially appealing for developers of safety-critical products, while MicroCOS 3 is a somewhat more dynamic kernel, offering a number of features unavailable from its predecessor. Micrium released MicroCOS 3 in 2009, having decided that an entirely new kernel with a core differing from that of MicroCOS 2 would be necessary to implement the range of feature requests that had been collected from MicroCOS 2 users during that kernel's time in the field. At the start, the new features available in MicroCOS 3 included round-robin scheduling, built-in performance measuring capabilities, and low-overhead task-based semaphores and message queues. Since its release, the kernel has been updated with a number of additional features, such as red zone stack protection, dynamic tick support, and an option for tickless operation. Users of MicroCOS 3 can control the kernel's features through an extensive set of configuration parameters. While MicroCOS 2 was highly configurable, its newer counterpart may be even more so, putting 3 configuration files at kernel users' disposal. In a few minutes, we'll see how the configuration files for both MicroCOS 2 and MicroCOS 3 can be used to optimize the kernel's memory footprints. However, we're first going to dive inside MicroCOS 2 and MicroCOS 3 to better understand the efficient schedulers on which the kernels are based. Scheduling is a frequent operation in a multitask system, so it is very important for a kernel's scheduling code to consume the minimum number of CPU cycles possible. The scheduling code in MicroCOS 2 has a very simple objective, and it's able to achieve this objective through a highly streamlined implementation. Every time MicroCOS 2's scheduler runs, its goal is to find the highest priority task in the ready state. In other words, the highest priority task that has not given up the CPU through a pending or delaying API call. To find this task, the scheduler simply scans the contents of an array. The array is expected to contain bits representing each of the tasks managed by the kernel, and it is updated whenever API calls result in a task's state changing. Within the array, bits with a value of 1 correspond to tasks that are ready to run, while bits with a value of 0 correspond to pending or delayed tasks. The scheduler then simply needs to start with the bit representing the system's highest priority and progress towards the bit for the lowest priority, examining each intervening bit and stopping when the first set bit is encountered. This process is accelerated dramatically using a helper variable that depicts the status of each element in the scheduling array, along with a ROM-based lookup table for rapidly converting an 8-bit value into a bit position for the first non-zero bit in that value. Thanks to such optimizations, the kernel is able to schedule a task using just 2 lines of C code in systems with a total task count of 64 or lower. Thus, in a MicroCOS2-based system, application code can utilize a larger portion of the CPU cycles than would be available with a less efficient scheduler. Like MicroCOS2, MicroCOS3 offers preemptive priority-based scheduling. Also, much like its predecessor, the newer kernel performs scheduling by scanning bits in an array. In the case of MicroCOS3, though, this process can be optimized either with a lookup table or through hardware-specific means. The latter often takes the form of a count leading zeros instruction, an assembly instruction that certain CPU cores offer for rapidly determining the bit position of the first set bit in a particular value. While MicroCOS2 only offers one type of scheduling, MicroCOS3 allows developers to select round-robin scheduling as an alternative to the preemptive priority-based algorithm. Under round-robin scheduling, a subset of a system's tasks share priorities, and those equal priority tasks each receive a portion of the CPU cycles. As with preemptive scheduling, the code for the round-robin scheduler in MicroCOS3 has been written so as to maximize the amount of CPU cycles available to application developers. Regardless of what scheduling algorithm a kernel uses, a common result of scheduling is a context switch, the process of passing CPU control from one task to another. Accordingly, this is another operation that should be performed quickly. A context switch involves saving and restoring CPU registers, and on a Cortex-M, both MicroCOS2 and MicroCOS3 are able to complete a context switch in just 50 CPU cycles. The kernel's combination of optimized scheduling code and efficient context switches gives developers a foundation for multitask applications that maximize the performance of the hardware on which they run. Along with CPU cycles, memory is another type of CPU resource that seems to be in increasingly short supply, even as the underlying technologies advance rapidly. Today's hardware platforms boast RAM and flash allocations that once would have seemed extremely generous, but that often end up looking meager in the face of complex design requirements. It is highly important, then, for developers to understand their system's memory requirements and to do everything possible to reduce those requirements. Although every kernel consumes flash and RAM, developers who select MicroCOS2 or MicroCOS3 for their projects give up very little in terms of memory space to gain the benefits of the kernel's multitasking capabilities. The code needed for a simplified multitasking environment can occupy as little as 5 kilobytes of flash in a system based on MicroCOS2 or MicroCOS3, and even robust configurations of the kernels consume no more than 15 to 20 kilobytes. RAM usage is similarly low for both pieces of software, with footprints of just 1 to 2 kilobytes the norm. Although it is the case that in addition to this space for the kernel's own data, a kernel-based application must set aside RAM for each of its task stacks, the amount of space needed to meet this requirement is mostly shaped by the complexity of the tasks and the needs of the CPU, as opposed to the kernel itself. While memory efficiency is, to a large extent, inherent in the designs of MicroCOS2 and MicroCOS3, there are certainly steps that developers can take to minimize the kernel's memory consumption for specific applications. Both kernels are highly configurable, with pound defines available to expand or scale back the implementation of any service. The next couple of slides highlight the configuration constants that have the most significant impact on memory footprint, and in particular, RAM usage. The pound defines seen here correspond to MicroCOS2, and are typically contained in the configuration file osconfig.h. The first two of these definitions, OS max tasks and OS max events, control the quantity of data structures to which the kernel will have access for the implementation of various services. OS max tasks sets the number of task control blocks, or TCBs, available to the kernel, and thus determines the total number of tasks that application code will be able to create. In a similar fashion, OS max events sets the quantity of event control blocks at the kernel's disposal, thereby establishing a ceiling for the number of semaphores, mutexes, message queues, and other objects to be managed by the kernel. To make the best use of a system's memory, application developers should ensure that these definitions accurately reflect the quantities of tasks and kernel objects required by application code. Developers should likewise check the size of their system task stacks in order to guarantee efficient usage of memory. A MicroCOS2-based system can include as many as 3 system tasks that work on behalf of the kernel, and the sizes of the stacks used by these tasks are determined by the final 3 pound-defines shown here: OS task timer stack size, OS task stat stack size, and OS task idle stack size. The kernel provides stack checking capabilities that developers can leverage to verify that the system task stacks, as well as the stacks for an application's own tasks, do not contain an excessive amount of unused or wasted entries. While the strategy chosen for the allocation of task control blocks and the data structures associated with various kernel objects in MicroCOS3 eliminates the need for configuration constants like MicroCOS2's OS max tasks and OS max events, the newer kernel still has plenty to configure. There are, in fact, 3 configuration files in MicroCOS3: osconfig.h, osconfigapp.h, and ostype.h. But pound-defines impacting RAM usage are mostly found in just one of these files, osconfigapp.h. A few of the most important RAM-related pound-defines are shown here. The first of these definitions, osconfig message pool size, establishes the total queue capacity capable of being managed by MicroCOS3. Message queues are the kernel's mechanism for inter-task communication, and application code is expected to manipulate queues through API calls. Each time an application calls the API function to create a queue, the kernel must set aside data structures to implement the queue's entries. The total number of these structures available for kernel use is determined by osconfig message pool size, so developers must make sure that the combined capacities of all the queues used by their code does not exceed the value of this pound-define. The second pound-define in the list shown here, osconfig ISR stack size, controls the size of the kernel's interrupt stack. Where allowed by hardware, MicroCOS3 employs a separate stack for ISR use, so the code contained in interrupt handlers isn't forced to rely on the stacks of interrupted tasks. For the most efficient use of memory, application developers should make sure that this pound-define truly reflects the stack requirements of their interrupt handlers. Developers of MicroCOS3-based applications should also confirm that their system task stacks are sized appropriately. As is the case for MicroCOS2, MicroCOS3 implements system tasks for performing a number of different kernel-specific operations. In the newer kernel, there can actually be as many as 4 of these tasks, and each has a pound-define to establish the size of the corresponding stack. The 4 definitions are osconfig timer task stack size, osconfig tick task stack size, osconfig stat task stack size, and osconfig idle task stack size. Like its predecessor, MicroCOS3 offers developers stack checking services to aid in determining appropriate sizes for each of the stacks. In addition to having control over the size of the system task stacks in MicroCOS3, developers have the option of eliminating these tasks altogether. The presence of the tasks, like the sizes of their stacks, is controlled through the kernel's configuration. By configuring MicroCOS3 so that it entirely lacks system tasks, developers eliminate 4 stacks and 4 TCBs from their system's RAM footprint, although the services implemented by these tasks are, of course, likewise eliminated. The ability to disable all system tasks is one of a number of relatively new features in MicroCOS3 intended to improve the efficiency of applications based on the kernel. While MicroCOS2, with its lengthy history in safety-critical applications and its popularity amongst developers of such applications, has not undergone any substantial changes in years, its newer counterpart has space to evolve in order to help developers face new challenges in embedded systems. In just the past few versions of the kernel, features have been added to address efficiency on multiple fronts. One type of efficiency that has not yet been covered in this webinar, but that helped motivate the development of some of MicroCOS3's new features, is power efficiency. Micrium has always supported customers whose systems have low power requirements, but the developers of MicroCOS3 have taken a more proactive stance on power management, beginning with the recently released version 3.05 of the kernel. In this version of the software, developers can establish a dynamic tick interrupt for their MicroCOS3-based systems, or eliminate the kernel's periodic tick interrupts altogether. Both of these features lower the CPU overhead imposed by the kernel and, as a result, minimize power consumption. Another area where MicroCOS3's developers have been seeking to lower overhead and increase efficiency is interrupt handling. The upcoming release of the MicroCOS3 kernel port for Cortex-M-based MCUs allows developers of kernel-based applications to write ISRs that are not affected by kernel-critical sections. These non-kernel-aware ISRs are intended to be free of MicroCOS3 specific code, and they operate with zero kernel-imposed interrupt latency. They represent yet another tool with which developers of MicroCOS3-based applications can maximize the performance of their code. With such features for eliminating overhead, and with the kernel's naturally efficient designs, both MicroC OS3 and MicroCOS2 are ideal choices for developers whose requirements make even the latest MCUs seem a bit cramped. The kernels have for years helped developers meet such requirements, and Micrium's team is continually at work improving the software to keep its users one step ahead of the latest challenges. In addition to incorporating the development of new features, this work includes seeking partners like Datalight, whose highly efficient file system software is a perfect complement to Micrium's kernels. With the combination of Datalight and Micrium, developers have a software platform capable of efficiently harnessing the capabilities of today's MCUs and accelerating the work of creating tomorrow's innovative products.
Thank you, Matt. Each of the previous topics, from efficient scheduling and memory footprint to eliminating unnecessary tasks, has a focus at the file system level as well. Reliance Edge is delivered in source code and provides built-in settings to eliminate file system features, saving memory and optimizing runtime. This file system's transaction point operations and deterministic I/O follow directly from Micrium's efficient scheduler options and have a further impact on the product lifetime. Finally, both MicroCOS and Reliance Edge come with a wide variety of tools to validate and measure performance. Choosing how many file system APIs to support is the first option for memory efficiency. If your design doesn't need subdirectories or even file names, Reliance Edge provides what are called file system essentials. With the FSE API, files are identified by a number rather than a path and file name. The number of files is fixed at compile time, and those files are created when the volume is formatted. They are never deleted. These files can be read from, written to, and truncated. This hybrid file system would be great for an environment that requires event logging and basic analysis, where a full file system is overkill. This sort of file system source code flexibility gives the developer near complete control over memory efficiency. On the next slide, we have some memory use comparisons for this configuration. Reliance Edge is memory efficient to start with, especially when you consider that it is fully reliable also. This chart shows the RAM usage and code size as it could be stored in ROM or other memory. Another option available between the file system essentials and a full POSIX environment is what we call small POSIX. In this configuration, rename is disabled, and Reliance Edge uses the minimum number of 6 buffers. These sorts of changes are relatively easy with the Reliance Edge source code. More details are available in our developer's guide for this option. The media block size affects not only the RAM usage, but also the maximum volume size and file size. Using a 4 KB block size, the maximum volume size is just under 4 terabytes, with a maximum file size of 1.3 terabytes, which is quite a lot for the Internet of Things. A full chart of block size options is on page 92 of the developer's guide. Reliance Edge uses transaction points for reliability. This means that all writes to the media are performed on the working state until a successful transaction point commits them to the known good state. Like any power fail-safe mode, these involve a little overhead. A configuration utility allows the developer to control how often transaction points occur, and thus control the overhead. This allows the designer and developer complete control over the file system side of the scheduler. The configuration tool defines how often transactions will be performed at compile time, but these settings can also be changed during runtime. A transaction mask is available through a simple API that allows changes at any time. These could be used to reflect any change in use case, for example, toggling the device between a resting and active mode. In addition to these automatic transaction points, a manual option is also available. To use this, an API is called to perform a transaction point when the developer's application chooses. One sample use for this would be a system update. In this example, the transaction mask is cleared and no manual transactions are performed until all of the system file updates are verified. Following that, a single manual transaction commits this new environment to the media, and then the previous transaction mask can be restored to allow the system to seamlessly continue. Between transaction points and file system overhead, the worst case I/O can be calculated, and these equations are also included in the developer's manual. While measuring some block devices deterministically is quite difficult, Reliance Edge allows the developer to plan for everything above the block device in fine detail. At mount time, Reliance Edge only ever reads 3 blocks from the media. These are used to determine which of the media states is the current or known good state. The developer's guide gives complete calculations for how many operations will be required for a transaction point, for a file read, or file write. The best way to verify changes to efficiency, along with validating the remaining API, is through tests. Reliance Edge is delivered with the source code for tests to measure those situations and help troubleshoot any problems. This source code can be found in the Tests subdirectory of the licensed Reliance Edge development tree. Only the FS Stress test is provided with the GPL v2 release. VDEV test measures performance of the block device, and FSIO measures the performance of the file system I/O. The API tests are used to validate each of the APIs and make sure they are all functional. These tests, by the way, are destructive and should only be performed on a volume which does not contain important data. Even so, they are an important tool in the hands of developers seeking to validate and optimize their design efficiency. Datalight has been providing solutions to keep data reliable for over 30 years. Having a solution provided in well-documented source code allows our customers to optimize their memory footprint and balance performance and reliability across the embedded industry. Like Micrium, we provide fast and efficient customer support, along with excellent documentation. A solution built with these 2 software products is really the best solution for efficiency and long product lifetime, and both companies provide solid tests and certification options.
Just as the test code available for Reliance Edge offers the file systems users a level of confidence that the software is running properly on their system, the certification deliverables available for Micro-C OS2 and Micro-C OS3 assure users that the kernels execute in a highly consistent, reliable manner. This reliability has for years drawn developers to Micrium software, much like the efficient resource usage covered in the earlier slides. Perhaps the clearest evidence of the kernel's reliability lies in the lengthy certification history of Micro-C OS2, which has been used in products certified according to a variety of standards, including aerospace systems meeting the lofty requirements associated with Design Assurance Level A of the DO-178B standard. Of course, delays in development don't arise as a result of software bugs or inefficiencies alone. Projects can also suffer from missed deadlines when developers don't fully understand how to use the kernel, file system, and other software modules in their system. Accordingly, a central requirement for Micrium has long been providing software that is impeccably documented and supported by a highly responsive team of knowledgeable engineers. Micrium software, in other words, helps to ensure efficient use of hardware resources, while it likewise promotes an efficient, hassle-free development process.